Welcome to The Explainer. Today we are exploring something absolutely fascinating and honestly, totally essential. We're talking about linear regression. We're going to see how we can go from understanding really basic data correlation all the way to full-scale model evaluation. To kind of ground our journey today, I want you to imagine a fictional online electronics retailer. They've got a massive inventory, a super dedicated marketing team, and some really ambitious growth goals. But like literally any modern business, they can't afford to just guess what their future looks like, right? They actually need to map it out using data.
So, let's ask a pretty high-stakes business question on behalf of our retailer. Suppose a company spends a lot more money on advertising. Can we predict exactly how much its sales will increase as a result? Now, this isn't just some academic exercise. When real money and return on investment are on the line, simply guessing or, relying on a gut feeling, that just isn't going to cut it. We need a solid mathematical way to look at our past advertising spend and confidently forecast our future sales.
Okay, let's dive into this. Here is our roadmap for the explainer. We'll start with the prediction problem and understanding data relationships, then move into simple linear regression and finding the best fit, and finally, we'll tackle multiple variables and evaluating model performance. Let's get started.
Section 1. The prediction problem, targeting a continuous number.
This right here is the foundational goal of regression. We aren't trying to predict a category, like say whether a customer will click yes or no. We want an actual continuous numerical output, whether we're predicting sales based on advertising like our electronics retailer is doing, or estimating house prices, maybe forecasting electricity demand, or figuring out insurance premiums. Structurally, they all share the exact same core goal. The target is always a number.
Let's move to Section 2 and see how this builds. Understanding data relationships, specifically direction and strength.
Well, before we can mathematically predict a number, we first have to identify the underlying relationships in our data. For our electronics retailer, we might see a positive relationship between advertising expenditure and sales. So as ad spend moves up, sales move up together. Makes sense, right? Conversely, we might see a negative relationship between product price and sales. As the price goes up, the number of units sold might go down. Understanding this direction is the absolute first step in organizing our data.
To put an exact number on this relationship, we can look at the Pearson correlation. It's this really useful statistical measure that ranges perfectly from -1 to +1. If your correlation is near +1, you have a very strong positive linear relationship, meaning they march upward hand in hand. If it's near -1, it's a strong negative relationship, and if it sits right in the middle near 0, well, that basically means there is little to no linear relationship between those two variables at all.
But here is a crucial trap we absolutely have to watch out for. Correlation is not causation. Just because our retailer's ad spend and sales move together doesn't automatically mean the ad spend directly caused those sales to happen. There could be totally hidden factors at play. Maybe general economic conditions just improved, or maybe a particular product went viral on social media, or actually, maybe it's just the holiday season. The variables definitely move together, but you must always remember that correlation alone just doesn't prove cause and effect.
Section 3. Simple linear regression, from observation to equation.
Now, what's really interesting here is that while correlation shows us a relationship exists, it still doesn't give us a practical equation to actually make future predictions. But we can take the classic mathematical formula for a line, y equals b0 plus b1x, and translate that into plain English business logic. So for our retailer, that becomes predicted sales equals 500 plus 20 times the advertising spend. We've literally taken an abstract algebraic concept and turned it into a direct, usable business forecasting tool.
So let's break down exactly what those numbers mean, starting with the slope. Here, our slope is 20. This means for every single $1 increase in our advertising spend, we can expect a yield of 20 more sales. The intercept, which is 500, means that even if our ad spend is exactly $0, the model predicts we will still naturally make 500 sales. But a quick warning here. Mathematical intercepts don't always have a practical real-world meaning. For example, if you're predicting the price of a house based on its square footage, the math will happily give you an intercept for a house with 0 square feet. Obviously, a house with 0 space doesn't exist, so you wouldn't bother pricing it. Always apply a real-world logic check to your intercepts.
Moving right along to Section 4, finding the best fit, minimizing the mistakes.
Now you might be wondering, with hundreds of data points, how does the algorithm actually know which specific equation is the absolute best line to draw? It figures this out by looking at its mistakes, which in statistics we call a residual, or a prediction error. A residual is just the vertical distance between the actual observed data point and the spot on the line where the model predicted that point would be. It's literally the gap between reality and the prediction. Now, if we just took all these errors and added them up, the positive errors above the line and the negative errors below the line would actually cancel each other out, which would make the model look perfectly accurate when it definitely isn't.
To solve this, we use the method of least squares. Instead of just adding the errors together, the algorithm squares them first. This is incredibly clever because squaring the numbers turns all the negative errors into positive ones, so they completely stop canceling each other out. Better yet, squaring heavily penalizes the really large mistakes. The algorithm then runs the numbers and selects the coefficients that minimize this total sum of squared errors. This ensures our regression line sits as snugly as mathematically possible right in the middle of our data points, giving our retailer the most accurate sales forecast possible.
Section 5, multiple variables and categories, expanding the model.
In the real world, our retailer sales depend on far more than just advertising, right? They depend on the price, the discounts, the season. We need a way to add more complex features into our model. To do this, we use multiple linear regression. Instead of just one X, we now have X1, X2, and so on. We are factoring in ad spend, discount percentage, and product price all at once. Geometrically speaking, we are no longer drawing a simple 2D line on a piece of paper. We're calculating a 3D plane or even higher dimensions. The real key takeaway here is how we interpret the coefficients now. The coefficient for ad spend represents its relationship with sales specifically, while holding all the other variables, like price and discounts, completely constant.
And this brilliantly illustrates another challenge. What happens when your data isn't a number? Algorithms cannot read text like north or high. They only speak math. So we use encoding. We use label encoding to transform ordered categories like low, medium, and high into sequential numbers like 1, 2, and 3. But for unordered categories like geographic regions, saying north is 1 and south is 2 implies south is somehow twice as much as north, which is absolute nonsense. So instead, we use one-hot encoding. This splits them into separate binary columns of zeros and ones, allowing the algorithm to seamlessly process text categories without getting confused.
Section 6. Evaluating model performance, our quality control.
Okay, so we've built our complex model. But before we bet the entire company budget on it, we must evaluate its quality using a few essential metrics. MAE, or mean absolute error, simply averages the distance of our mistakes. RMSE does exactly what we talked about earlier. It squares the errors to harshly penalize any massive outliers. For both of these, lower is always better. MAPE translates these errors into a percentage, which is often way easier to explain to business stakeholders. Then we have R-squared, which tells you the percentage of variance the model actually explains, where higher is better. But be careful here. If you just keep blindly throwing random variables into your model, regular R-squared will artificially inflate. That's exactly why we use adjusted R-squared, which actually penalizes you for adding useless, overly complex variables to the model. And there you have it, the complete workflow end-to-end. We started with a business problem, predicting sales for our retailer. We collected the data, explored the relationships to ensure correlation, prepared our numerical and categorical variables, built the regression model to generate predictions, and finally evaluated the errors for quality control. This is the exact journey from a blank slate to a fully evaluated regression model.
Which leaves us with one final thought. If this explainer helped you learn to confidently predict the numbers, what hidden relationships will your own data reveal next? The power to forecast the future is quite literally at your fingertips. If you found this valuable, join us for our next explainer, where we'll take everything we just learned and build this exact model step by step using Python. I can't wait to see you there.